Thanks for the presentation, Mike. Please continue submitting your questions in the Q&A. We'll get back to those after the end of the session today. Our next speaker will be Joey Burns, speaking on water testing and EPA methods. Joey is a chemist with expertise in the manufacturing and documentation of aqueous metallic standards. His experience includes bulk scale reactions, purifications, and C of A and SDS generation. In addition, he has many years of experience in custom CRM manufacturing. Joey received a bachelor in chemistry from Virginia Tech.
Hello, my name is Joseph Burns, and I'm the production manager here at Inorganic Ventures, meaning I have years of experience in solution preparation and documentation. Thank you for joining me on my talk about the analysis and sample preparation considerations for EPA testing methods 200.7, 200.8, and 6020. Together, we'll be looking at some EPA definitions, some sample preparation advice, sources of impurities within your lab, and some general causes for analytical heartache. I hope to share with you some things that I've learned through years of practical experience in preparing samples and looking at instrument data. The EPA breaks down water into 4 different major types, and not all of the types of water are the same. There are guidelines that pertain to the type of water you are testing, so you need to make sure that you know what types of samples you are working with so that you can be aware of any special regulations or guidelines that may apply. The EPA does not regulate private wells, but they can monitor a privately owned system if it serves at least 15 service connections, or on average, at least 25 people for at least 60 days of the year. A service connection is defined as each building serviced by the same non-community water system. The EPA is concerned about 4 different types of contaminants: any physical, chemical, biological, or radiological substance in the water. Basically anything other than a water molecule. A physical contaminant is a sediment or suspended organic material from sources such as soil erosion. Chemical can be either man-made or natural. Biological contaminations, which are slightly outside the scope of this presentation, and radiological elements that can emit ionizing radiation such as uranium or thorium. The EPA 200.7 method is an ICP OES method that looks at the total dissolved solids of the 32 elements highlighted in tan. As the only ICP OES method that will be discussed in this presentation, there is more leeway in the concentrations and your total dissolved solids levels can be higher. While mercury is an analyte of interest in both this method and 200.8, these methods are not suitable for testing organomercury compounds. Cerium is included not as an analyte of interest, but rather to help correct for any interelemental spectral interferences. As I'll discuss in more detail later on in this presentation, if boron and silica are present in your samples, the use of plastic labware is of the utmost importance. It is also important to note that this method is not suitable for determining the silica concentrations from solids. EPA method 200.8 is an ICP mass spec method used for the determination of the total recoverable analytes in aqueous samples and solids that have undergone digestion prior to analysis. Since the method requires the use of pneumatic nebulization, it is not suitable for analytes not in solution, such as suspended soils, sludges, and sediments. This method specifically focuses on the 21 elements in blue. You will notice that it covers many of the same elements as 200.7, but removes several of the alkaline earth metals and metalloids while adding thorium and uranium for radiological testing. EPA 6020A is another ICP mass spec method. It introduces back some of the alkali and alkaline earth metals, bringing our number of elements of interest up to 23. As I will discuss later in the presentation, the 6020 methods, so both A and B, require the use of an internal standard, and the EPA recommends options such as 6 lithium, 45 scandium, 89 yttrium, 103 rhodium, and 159 terbium. If you do choose to use 6 lithium, it must be sourced from an enriched material so that the isotopic interferences from the natural abundances of lithium are minimized. As written, EPA 6020B focuses down to the 12 elements on the ICP mass spec. But 60/20 does allow for an analyst to test analytes not explicitly listed in the method if the analyst can validate the accuracy and precision of the method in the waste to be analyzed. A thing to be aware of for all of these testing methods, not just 60/20B, is that since we are dealing with such low levels of testing, the EPA says to use ultra-high purity chemicals and acids in your sample preparations. Among all the methods we will be covering, these are the analytes that will be covered. As you have noticed that there is quite a bit of overlap in the analytes of interest. We will discuss some sample preparation considerations, potential interferences, and the different types of solutions that are called for in these testing methods. While this talk is focused around EPA water testing methods, a lot of the information can be applied to other methods as well, and can even potentially help you with your validation on expanding 60/20 to meet your individual lab's needs. On our website is the IV periodic table. It is an invaluable resource that consolidates much of the information that we'll be going over into one quick and easy to access location. Each element that we work with has its own subpage referencing compatibility issues, stability information, preparation advice, as well as suggested spectroscopic information and warning about various interferences. As you can see, I chose aluminum as an example, but it goes wide across the board, and anything that doesn't have an X on it has detailed information. Before you can even think about testing your samples, you must first prepare them. There are many considerations that you'll need to take into account while preparing your samples. Your matrix composition is a major concern that you must take into consideration before you start anything. Most of the elements covered by this testing methods will be stable in a simple nitric or hydrochloric acid matrix. 4 of them, however, prefer a matrix that contains at least trace amounts of hydrofluoric acid. This can be troublesome as it will introduce compatibility issues, and very importantly, some labs will not allow hydrofluoric acid in them for safety reasons. Antimony can be preserved in tartaric acid, but the total nitric acid concentration should not exceed 2%. In addition to this, mercury will not be stable in the same solution as tartaric acid, as the tartaric acid will cause the mercury to reduce and the mercury will fall out in metallic form. Molybdenum on its own is stable in nitric acid or hydrochloric acid, but if it is mixed with any of the elements that require hydrofluoric acid for stabilization, such as antimony, silica, tin, or titanium, it will steal away the hydrofluoric acid from these elements, causing them to crash out. Aluminum, arsenic, boron, phosphorus, and selenium will also do this. In addition to the safety concerns, hydrofluoric acid presents compatibility and long-term stability issues. In general, alkali earth metals and rare earth metals can form insoluble fluoride compounds. Scandium is fortunately more tolerant to hydrofluoric acid, which allows it to be commonly used in internal standards solutions with elements such as germanium, but we'll discuss that a little bit more later. Due to the sensitivity of some elements to hydrofluoric acid, order of addition matters. You may find something goes into solution smoothly if you add hydrofluoric acid at the beginning and your sensitive elements at the end. But if you try to add the same elements immediately after adding your hydrofluoric acid, you may find yourself with a snow globe. It is also important to note, it's not just hydrofluoric acid that can cause these kind of compatibility issues. We have found that barium can be very sensitive to high levels of nitric acid. So if you add your barium immediately following your nitric acid, you may also find a lot of precipitate form. We have found that in nitric acid only matrices, that about 1 ppm of mercury will absorb onto the sidewalls of plastic containers. This is not a big deal if you're looking at a 10,000 ppm standard for mercury, but if you're looking at a sample that only had 1 ppm of mercury to start with, it is suddenly a very big deal. If you do use gold to stabilize the mercury, you'll need to watch out for your matrix. While most of our gold standards are stabilized with hydrochloric acid, we do offer gold standards in nitric acid to be used for this purpose. If you're analyzing silver and hydrochloric acid, You will likely need to complete an in-house stability study of your working solutions. Silver and hydrochloric acid is light sensitive, and the ratio of hydrochloric acid to silver is very important. We tend to preserve standards containing 10 ppm silver and 10% hydrochloric acid. We do understand that this is a high concentration for the system, so we recommend you reduce the hydrochloric concentration until you observe an acceptable usage period for you. It is typically not feasible to produce silver in low hydrochloric acid, as the stability is very short, and if you need to use hydrochloric acid, you may want to consider purchasing a higher concentration of silver and nitric acid to dilute in-house. We have found that using thallium oxide as a starting material, the thallium will be stable in hydrochloric acid, whereas thallium +1 from thallium nitrate is unstable even in super trace amounts of hydrochloric acid and will cause it to crash, which brings back the importance of mining the matrix if you use gold and hydrochloric acid to stabilize mercury. Once you're ready to start preparing your samples, you will need to be aware of lab environmental contaminants. Even the cleanest of labs are subject to contamination from what is used inside of it. Pipette tips can be a major source of contamination, but we have found that leaching them in 1% nitric acid for about a week can pull out most of the impurities. More low-level mass spec work, you may want to consider a more robust leaching process. This can be achieved by heating the leaching pipette tips in an oven at about 60 degrees Celsius. When you purchase your reagents, you'll need to make sure that you have a good impurity profile on these. This can either come from the manufacturer, such as our TMI reports, or from your own in-house impurity testing. Believe it or not, we have found that calcium surface contamination from whey boats can be enough to cause the calcium number to deviate substantially in low-level solutions. We do not recommend the use of glass. It can contain high levels of sodium, aluminum, boron, barium, and calcium and potassium, and lower levels of iron, nickel, zinc, and strontium. Even after leaching, we have observed measurable concentrations of these. You may run into issues, particularly if you're measuring mercury in a nitric acid matrix. In addition to higher levels of potential contamination, if your sample has even traces of hydrofluoric acid in it, the acid will start to eat your labware, causing the boron and silica values to come out higher than they should due to leaching from your equipment. Something to note that can be a little surprising is that even just the fumes from hydrochloric acid can be problematic for low-level silver concentrations. We've observed that environmental hydrochloric acid fumes can cause issues for silver even if it is not actually added to the solution. The fix for this is to just not prepare low-level silver samples in the same hood as an open bottle of hydrochloric acid. Tubing, as something that is always around your instrument, is easily overlooked. Contamination can be a result of washout issues and memory effects. To mitigate this, you can perform a special rinse or simply just replace the tubing altogether, which should really be done frequently anyway as good lab maintenance practices. Much like your tubing, the sipper in your introduction system is a potential source of contamination if you do not rinse it in between samples, whether this is done manually or is automatically programmed if your instrument is equipped with an auto sampler. Once you have your sample into your instrument, you're not home free quite yet, as there are still many concerns that you'll need to take into account. One that can arise with EPA method 200.7 and ICP OES in general is the ionization of your group 1 elements, resulting in incorrect data. Ionization effect can get worse as the atomic number of the alkali element increases. We have had good results by spiking our samples with the cesium ionization buffer solution. This ionization buffer will flood the plasma with an excess of electrons, and this will reduce the relative abundance of the alkali metal ions, resulting in much better results. It's a simple fact of life that I'm sure that everyone listening to this presentation has experienced. Both OES and mass spec instruments will have issues with cross-elemental interferences. Earlier, I showed the elemental spotlight page on aluminum from our interactive periodic table. The reason I chose aluminum was so that you could quickly see how on method 200.7, the OES spectral interferences on aluminum line 396 1.152 nanometers can be quite severe due to a molybdenum interference. The easiest example to give for mass spec, not just for the EPA methods, but mass specs in general, is at mass 40. This at first glance would seem like an ideal place to check for calcium until you take into consideration that your argon gas will also be showing up at mass 40. The interactive periodic table on our website will list several interferences for each element that'll not only help you make good line or isotope choices, but it can give you guidance on what your interferences may be. An easy way to check if your polyisotopic elements agree with each other is to simply divide your counts by the natural abundance percentages of each isotope. And if those are not in agreement, then there's a very strong chance that you're dealing with a polyatomic interference. If you're working with a monoisotopic element, life will be a little bit more difficult, and you'll have to look very closely at the counts of elements that share that mass. There are ways to help you take into account these interferences before you even start looking at your data. Interference check solutions allow you to see exactly how the elements are interacting with each other without the added headache of trying to figure out your concentrations in an unknown. The methods have general guidance on the composition of interference check solutions, but advise that these can be modified depending on which analytes your specific laboratory are analyzing. All of the methods have discussed, you as an end user are responsible for all validation of any in-house methods you design. When validating your method, we recommend analyzing single element standards for every element you reasonably expect to be present in your samples. Once you have reviewed the spectra and characterized potential interferences, you can start to mix the elements together to more closely mimic your personal real-world samples. Here we have an example of interference check solutions that we offer. As the names imply, these products are explicitly designed for the 60-20 method. We do have 3 different versions of these products that are slightly different in order to work with different revisions of the method. There are 2 parts to this process. Part A is a synthetic matrix. It contains analytes that you are not particularly interested in, but need to run in order to get an interference baseline. Part 2 is a spike solution, and it is full of the analytes that you are interested in. The initial step is to run your synthetic matrix, get the background that I mentioned earlier. After you have this data, you'll need to take an aliquot of your synthetic matrix and spike an appropriate amount of solution B in order to determine the effect of A on B. Purity is of the utmost importance in this process. If you do purchase this from a supplier instead of making your own, you'll need to make sure that they provide a trace impurity analysis. Much like a musical instrument, your lab instruments will need to be regularly tuned in order to ensure that you are actually making music, or usable data in our case, instead of just noise. Each manufacturer has recommended solutions to use in order to complete this vital function, and you will find that they can be specific down to the instrument, not just the manufacturer. On our website, we have an instrument cross-reference guide that can help ensure your instrument produces the best possible data it can. If you find that your instrument is having troubles tuning, it is definitely time to consider doing some maintenance. Blink solutions are required in order to ensure that any background noise can be accounted for in order to ensure you have the best data possible. There are several types of blinks, and each of them have important roles to play in your analysis process. The calibration blink is exactly what it sounds like. It's just a matrix-matched water sample in order to help account for any trace impurities in your acid. The lab reagent blink is used to determine if method analytes or other interferences are present in the laboratory environment, reagents, or apparatuses. The lab fortified blink is a sample of the lab reagent blink to which known quantities of your analytes of interest are added at a suitable concentration. This will ensure that the methodology is in control and ensures that your laboratory is able to make precise and accurate measurements. The rinse blink should flush any previous samples and will help determine if there are any cross-contaminations between the samples. Making a 1000 ppm stock solution for each element you are working with can be rather cumbersome. There is the responsibility that you verify that each of these element concentrations are 1000 ppm, and you have to manage stability in-house. Purchasing these standards from a CRM manufacturer can help you have more confidence in your standards, and we can help you with your audits as well by proving a certificate of analysis and expiry period based on real-world testing data. Standards produced under our ISO 17034 are traceable to NIST or the SI system of units, which gives you the added confidence that the solution is actually what it says it is. When mixing elements, there are stability and compatibility issues that should be considered. We can help this by preparing the standards for you, or you can work with our chemists to make your own from stock singles. The EPA method recommends splitting elements into 4 to 5 different blends, but based on element concentrations, we can typically fit more elements into one solution. The final concentration guidance is rather vague, and it only says dilute to the appropriate working levels of the instrument, and that will need to be determined in-house. Leslie Owens has a talk focusing on uncertainty this week, so I highly recommend that you watch that presentation for a more detailed dive into uncertainty. As I touched on in my slides introducing 60/20, an internal standard is a requirement for the testing method. The methods have general guidance on composition of the internal standard solutions. If you're making any modifications to the method, you may find that it's necessary that the internal standard should be modified accordingly. And just as a friendly reminder about the importance of validating any in-house changes you'll need to make. Elements commonly used as internal standard elements are chosen based on these 3 criteria. They are not commonly present as an analyte in your sample. They'll need to be stable in your sample. It doesn't make a whole lot of sense to try to make a standard of silver and hydrochloric acid when the result you get in one run can and will precipitously drop in the next. And there should be as few interferences with your analytes as possible. There's not really a point in starting yourself off with a hindrance if you can prevent it in design. I just want to quickly go over a real-world example of an internal standard that we have designed for method 200.8. None of the elements in this standard are analytes of interest in method 200.8, and they're unlikely to be found in the samples that you'll be testing anyways. All of the elements included are stable in nitric acid matrices. We've chosen to stabilize this in a 5% nitric acid matrix. And with the exception of indium, all of these analytes are monoisotopic. Indium does have 2 major isotopes that we can look at the mass spec. Its major mass of 115 only has a minor interference of 10, which is not an analyte of interest in this testing. Mass 113 does have some issues with cadmium, but we have found in our lab that 115 gives solid enough data that we don't even need to worry about the interference on 113. Different instruments implement internal standard solutions differently. You will need to determine your instrument's requirements and operate as required. We have used some instruments that will automatically detect what elements are present in the internal standard and make adjustments accordingly. We've also used some instruments that require a very specific blend of elements that must be used as designed by the instrument manufacturer. While automated internal standardization is of course the easiest, it's not always available as an option, so you will have to do manual calculations using the shown formula. Of course, this is a situation where Excel or similar products are your friend, as they can help reduce human error from calculation to calculation. You will have to be careful, as this can introduce a systemic error if there is a problem with your program formula. Quality control samples are extremely important, as they can help you verify your standards. We do have the ability to manufacture second source standards. These can be manufactured as different lots prepared from the same starting in-house concentrates, or a different lot prepared from different in-house concentrates. Our starting materials are typically fixed due to stability, purity, and compatibility considerations, such as the thallium oxide and thallium nitrate considerations I mentioned earlier. So we usually cannot meet requests for standards prepared from a different lot or form of starting material. What does second source mean to you and your organization? Well, hopefully Leslie's previous talk can help you decide that. I would just like to take this last chance to remind you about the interactive periodic tables on our website. as it can help you pinpoint specific interferences you may be having on either your OES or mass spec instrumentation. Also, our sample preparation guide, as well as our instrument cross-reference guide, can help provide invaluable guidance. Please be sure to bring any questions you may have to our roundtable discussions. Or if you'd prefer to discuss a question via email one-on-one, please feel free to reach out to us at info@inorganicventures.com. And I would like to thank you for listening to my presentation.